Welcome back to the Deep Dive. Today, we're taking you right into, well, the really high-stakes world of industrial maintenance. We're looking specifically at this huge challenge. How do you prevent those catastrophic failures in critical infrastructure? Think power grids, gas pipelines, things we all rely on. And, the costs aren't trivial. We're talking staggering amounts when things go wrong because a tiny warning sign was missed, a micro crack maybe, or a faint electrical noise. Let's just start with a real nightmare scenario. You probably remember the 2019 California Kincaid fire, huge, destructive, and it all traced back to just one single transmission line fault. The liability for PG&E, get this, $13.5 billion.
Yeah, $13.5 billion. That number really drives home the stakes, doesn't it? A single missed signal in high voltage systems can just, well, escalate incredibly fast. So our focus today is on a specific solution designed to catch those tiny warnings before they become, billion-dollar emergencies. It's called the MD-1000. It's really aiming to set a new standard in high voltage and gas safety using a mix of AI and advanced sensor fusion.
Okay, so the mission for this deep dive, for you listening, is to really unpack how this MD-1000 tech tackles a fundamental problem that's kind of plagued asset management for years. The source material calls it the data disconnection problem. Let's get into what that actually means.
Right. To get the solution, you first have to grasp the problem with the old ways. See, when critical equipment starts to fail, it usually goes through two distinct phases. But the traditional diagnostic tools, they tend to capture these phases separately. They don't connect the dots.
Okay, so two phases. What's the first one? Let's call it the whisper.
The whisper, I like that. Yeah, that's the initial defect stage. We're talking microscopic things here. Tiny cracks, small gas leaks, or something really crucial called partial discharge, or PD.
Partial discharge. I've heard that term. What exactly is it for people who might not know?
Think of it like a tiny, tiny spark happening inside the insulation of high voltage gear. It's not a full short circuit, not yet. But it's actively eating away at the material, degrading it from within. And here's the kicker. Our sources say PD is behind something like 80% of all major power faults.
80%? Wow.
Yeah, it's huge. And this whisper stage, this PD, is best picked up using highly sensitive ultrasonic technology. You're basically listening for the high-frequency sound of that tiny spark.
Okay, so that's the whisper. What's the second phase? The scream.
Scream, exactly. This is when things get serious, the terminal defect stage. The erosion from the PD has gone too far. Now you're seeing overheating, serious degradation, thermal breakdown, often driven by something called joule heating. It's getting hot.
And this is where thermal imaging comes in, right? You can actually see the heat.
Precisely. Thermal cameras are great for spotting the scream. You see the visual sign that things are breaking down, potentially melting down.
So whisper detected by ultrasound, scream detected by thermal. What's the disconnection then?
That is the diagnostic gap. When you measure the whisper and the scream separately, maybe weeks apart with different tools, you just get two isolated snapshots. You might confirm, there's some PD activity, and later, there's a hot spot. You can't answer the most critical question.
Which is?
How fast is this initial PD whisper turning into that catastrophic thermal scream? You see the problem. The data points are disconnected in time and context.
Got it. So you know something is wrong, but you have no idea about the urgency. Is it going to fail tomorrow or next year?
Exactly. You can't accurately forecast the life expectancy, the remaining useful life, or RUL. You know there's a defect, but you don't know its trajectory. Is it stable? Is it accelerating rapidly?
Which means you can't really do predictive maintenance. You're still stuck reacting, maybe just scheduling things based on averages, not the actual condition.
You've hit it. Traditional methods giving notification, maybe, but not a reliable prognosis. That data disconnection keeps you stuck in reactive mode.
Okay, makes sense. So how does the MD-1000 claim to fix this? If disconnection is the problem, the solution must be connection, right?
That's the core idea.
Right.
The MD-1000 introduces what they call fusion diagnostics. It's not just using separate tools anymore. It integrates ultrasonic, thermal, and optical sensors into one single device. And here's the crucial part.
What's that?
It captures data from all three sensors at the exact same microsecond timestamp, perfectly synchronized.
Okay, simultaneous capture. That sounds technically challenging, getting sound waves and infrared radiation lined up perfectly.
Oh, it is. It's incredibly difficult.
Yeah.
But even that perfect capture isn't enough on its own. You need something to make sense of all that fused data.
The brain of the operation.
Exactly. And that's the AI cross-analysis algorithm. Now, what's really fascinating here is the data set they use to train this AI. It's been trained on over 1.5 million real-world fault data points, accumulated over 12 years, mostly from KPCo, that's the Korea Electric Power Corporation.
Whoa, 1.5 million failure examples.
Yeah.
That's not a lab simulation. That's real-world experience baked into the code.
Precisely. It's a massive library of what failure actually looks and sounds like. So the AI's job is pretty complex. It has to quantitatively correlate the intensity of the PD sound, the whisper, with the precise thermal change, the heat signature that's happening at the exact same moment because of that PD.
So it links the cause, PD, and the effect heat directly in real time.
Yes. By doing that cross-analysis, it can map the defect's trajectory. It understands how aggressively the PD is causing damage and generating heat. And that mapping is how it estimates the remaining useful life. It gives you a verifiable, actionable prediction. And this specific fusion method, it's patented, by the way.
Makes sense. So all this complex AI analysis, how does it translate for the person actually using the device out in the field? Is it complicated?
Actually, no. That's another key point. The source material highlights the one-click
Oh,
function.
click. Sounds simple.
It is. For the operator, you basically point-click, and in less than a minute, the device performs the fusion, runs the AI analysis, and gives you an expert-level assessment. And the output isn't just, good or bad. It uses a 6-stage precision classification system, grades A through F.
Okay, A to F. That sounds more useful than just pass-fail. Can you give an example? What's the real difference between, say, a grade C and a grade E?
Good question. It's about actionable intelligence. So grade A or B, that's minimal issue. Maybe check it again next year. But a grade C, the system might say, action recommended within 3 to 6 months. Okay, so you schedule it for the next planned outage. Manageable. But a grade E, that's critical. The recommendation is action essential within 2 weeks to 1 month. That's an immediate flag. It forces you to prioritize resources right now.
Right, so it takes the guesswork out of maintenance scheduling. It tells you what needs fixing and how urgently.
Exactly. It turns complex sensor data into a clear maintenance priority list that optimizes resources and, crucially, prevents those unexpected, costly outages.
Okay, let's shift gears a bit. We need to talk about the environment these things operate in. Substations, factories, turbine halls. They're incredibly noisy places, right? Like 80, 90, even 100 decibels of constant noise. So the title for this section is Hearing the Unhearable Signal. How on earth does the MD-1000 find that faint whisper of partial discharge amidst that industrial roar?
Ah, yes. This is, well, the ultimate challenge for any acoustic diagnostic tool. And this is where the MD-1000's hardware design really differs from some major competitors, like, say, the Fluke i910 acoustic imager.
Okay, tell me about that difference. Why not just use a big array of super sensitive digital microphones? That seems like the modern approach.
It does, and that's what many competitors do. They often use large arrays of digital MEM sensors. And look, those systems are great for creating those visual sound maps, quickly acoustic visualization. You can see where sound is coming from over a wide area.
But there's a downside for this specific task.
There can be, yes. The issue with purely digital sensors, especially when you're hunting for extremely faint, high-frequency signals like PD, is something called quantization noise.
Quantization noise. Explain that a bit.
Okay, think of it like this. An analog sound wave, especially a complex one like PD, is smooth and continuous. A digital system has to chop that smooth wave into steps. It quantifies it. Every time you do that chopping, you lose a little bit of the original detail, the fidelity. It's kind of like saving a really detailed photo as a low-quality JPEG. You lose nuance.
And that loss of nuance, that noise, makes it harder to pick out the really tiny signal.
Especially at a distance, yes. That quantization noise can obscure the very faint microsignals you're looking for, particularly when the source is, say, 50 meters away or more. Digital MEMS arrays are often better suited for louder leaks or closer sources.
So the MD-1000 went a different route with its sensor.
It did. They use a custom 3-layer hybrid analog ultrasonic sensor. The whole philosophy is different. It's focused on preserving the integrity of the original analog signal before any digital processing. It prioritizes the quality and fidelity of the raw signal capture over just painting a wide picture. This high sensitivity is what allows for that potential 50-meter-plus detection range for tiny signals.
Okay, so the analog sensor helps it hear the faint signal better. But we still have the 80-decibel turbine roaring in the background. How does it separate the signal from that overwhelming noise?
Right. That's where their patented AUNC technology comes in active ultrasonic noise cancellation. This isn't just passive filtering. Because the MD-1000 uses multiple high-fidelity analog sensors, it can actually dedicate some of them to specifically identify and characterizing that constant background noise, the turbine roar, the machinery hum.
Ah, so it listens to the noise itself.
Yes, it actively analyzes the signature of the interfering sound waves. Then, like those high-end noise-canceling headphones, but for complex ultrasonic data, it effectively subtracts that noise signature from the overall input signal, leaving, hopefully, the clean, clear signature of the actual defect, the partial discharge, even if it was initially buried in noise. The sources claim this gives them about 30% higher signal accuracy in really noisy places compared to systems without this active cancellation.
The proof, as they say, is in the pudding.
Yeah.
You mentioned that Korail anecdote earlier, the Korean rail operator.
Yes, that's a fantastic real-world example. They were testing on an old railway insulator, a known noisy environment. A competitor's acoustic camera, a well-respected one, scanned it and found nothing, missed it completely.
But the MD-1000.
An earlier model of the MD-1000 scanned the same insulator and successfully detected a tiny 2.4 dB partial discharge. That's incredibly faint, almost silent against the background.
Wow.
That really highlights the difference, you see. It's that focus on analog fidelity and active noise cancellation, allowing it to pick up microsignals that others might miss. It heard the whisper when the other system couldn't.
Okay, this is where it gets really interesting for people managing budgets and operations. Let's connect this technical edge to the bottom line.
Yeah.
Talk about the quantifiable ROI, the results this tech has shown globally.
Right, let's move from the how to the so what. We're looking at verifiable key performance indicators, KPIs. The overall defect detection rate is cited as 99% plus metal same, which is table stakes, really. But the really impressive figure is the fault prediction accuracy, that RUL forecast we talked about. The sources state it's 87.4%.
87% accuracy on predicting remaining life. That's genuinely predictive then.
It really is. It means when the system flags something as grade E, needing action in 2-4 weeks, it's right almost 9 times out of 10. That builds trust and allows for confident planning.
And what about efficiency? Did users like KPCO see time savings?
Huge savings. KPAC reported that their diagnosis time per asset dropped by 73%. It went from about 15 minutes down to just 4 minutes.
15 down to 4. Multiply that across thousands of assets.
Exactly. The labor savings alone become significant very quickly.
And that prediction accuracy must translate into safety and cost savings too, right? Preventing failures.
Absolutely. That's the ultimate payoff. When you can predict failures accurately, you can intervene before they happen. This led to a reported 65% reduction in unplanned outages. Fewer outages mean less downtime, less emergency repair costs. The sources suggest overall maintenance costs can be reduced by up to 60%, and by catching things early and fixing them properly based on the 6-stage grading, you can even extend the asset's lifespan, they quote, by about 18%.
Those are some compelling numbers. Let's look at a specific case where that fusion capability really shone. The HE Hyundai Electric example. The unsolvable leak.
Yes, that's a great one. They had this transformer built for export, and it had a persistent, absolutely tiny nitrogen gas leak. Microscopic. They'd already thrown the standard tools at it, a good quality Fluke ultrasonic leak detector, a high-end FLIR thermal camera. Neither could pinpoint the source. It was just too small, too diffuse maybe.
So enter MD-1000.
Right. They brought in the MD-1000, used its synchronized fusion diagnostics, combining the faint ultrasonic signature with any minute thermal variations in visual data, and they found it. Solved the unsolvable leak. It really proved the value of that simultaneous multi-sensor approach for tricky, low-level defects.
And let's circle back to where we started public safety, preventing disasters like Kincaid. This tech was actually used in the U.S. after that fire, wasn't it?
It was, yeah. Following the Kincaid fire, PG&E launched a massive inspection project for their distribution lines. The MD-1000 was deployed as part of that effort. Its job was to scan vast lengths of power lines, looking for those early warning signs, those potential ignition sources.
And the result?
The overall project, which the MD-1000 contributed significantly to, identified some 640 potential hazards across the distribution network that required immediate attention or mitigation.
640 potential Kincaid-like situations found before they could ignite.
That's the idea. Finding those weak points, those PD whispers, those potential overheating spots before they fail catastrophically. And look at KPICO in Korea. Over 5 years of using this tech, they saw a 58% drop in power outages. That's a direct benefit to the public.
So it sounds like this isn't just another inspection tool. It's more fundamental than that.
I think so. The way the sources frame it, the MD-1000 represents a real shift, moving away from just reacting or even just following a maintenance schedule towards genuine, data-driven, predictive intelligence. They position it as an intelligent edge node. It's out there, right at the asset, collecting this incredibly rich, fused, high-fidelity data.
And feeding that data somewhere.
Exactly. Feeding that high-quality insight into a larger system, maybe an industrial integrity platform, allowing for a much smarter, holistic view of asset health across the entire grid or plant.
Which logically leads to the future, right? Where does this go next? Automating the whole process.
That seems to be the roadmap. The sources talk about moving towards autonomous diagnosis systems. Think about MD-1000 units mounted on drones, for instance. They could inspect miles of transmission lines or large, hard-to-reach substation components automatically without direct human intervention for the initial scan.
And the business model might shift too.
Yeah, there's mention of moving towards diagnosis as a service, or DISAS. So instead of buying the hardware, customers might subscribe to get the diagnostic insights, the real-time integrity data delivered to them.
So the tech keeps learning, the AI gets better, and the goal is full autonomous monitoring of our critical infrastructure. Makes sense. We started this deep dive talking about that staggering $13.5 billion cost from the Kincaid fire, all traced back ultimately to a small fault, a little noise that wasn't properly heard or understood in time. The evidence we've discussed today suggests the technology now exists to actually hear those quietest warnings, even in the middle of industrial noise.
And not just hear them, but analyze them, fuse the data, and provide a pretty accurate prediction of when action is needed.
It changes the game, doesn't it? Knowing when something needs fixing, not just that it needs fixing.
It fundamentally changes the risk calculation, yes. For utilities, for heavy industry, knowing the RUL with high confidence is huge.
So here's the final thought for you, listening. Given what we've heard about fusion diagnostics, about active ultrasonic noise cancellation, about the ability to get an 87% accurate prediction, what is the real cost for your organization of not listening to those quietest warnings? What's the price of missing the whisper before it becomes a scream? That's something to really mull over. Thanks for joining us for the deep dive.